Welcome to Module 3, Systems of Equations and Inequalities. Solutions to equations and inequalities. When I say solution, I just mean an ordered pair that lies on the graph and satisfies the equation or inequality. So for example, this first one, y equals 2x minus 4, how many solutions do you think that equation has? A lot of people were guessing 2 or 1. The answer is actually infinity. It has infinitely many solutions. And the only way that we can really even write all of the solutions is to draw them. The ordered pairs that work in this equation, if we plotted all infinity of them on a graph, they look like a line. So that's why we call this the graph of that line, because it graphs all of the solutions. So if I were going to check to see if 0, 0 is a solution to that equation, there's two ways you can do it. The first way is by plugging in x equals 0, y equals 0 into the equation and seeing if that's true. Does 0 equal negative 4? And it doesn't, so we would know that 0, 0 is not a solution. We could also tell on the graph that 0, 0 is not a solution because it is not on that line. Remember, all of our solutions are points on that line. So for each of these, I just want you to plug in the x and the y. And in this case, 2 does equal 2. So we would say 3, 2 is a solution. And if we looked at that on the graph, we can see that the point 3, 2 is on the graph of the line. So that's another way that we could tell that it's a yes. So if I'm asking you to check using the equation, I'm looking for you to show your work, or I'll probably say show your check. If I don't give you an equation and I give you a graph, then it's fine just to plot the point. For example, if it was 5, 3, you would plot 5, 3, and you could just say no without showing any work. If I gave you the equation, I'd want you to plug in the x and the y value. Again, I call this showing your check. Does 3 equal 6? And then we would know that this one's a no as well. Let's talk about inequalities. Inequalities also have infinitely many solutions. You'll notice that this is the same like y equals mx plus b is the last one, but instead of y equals, it's y is greater than 2x minus 4. So it's the same graphed line. Did you notice that it's a dotted line? The reason that this line is dotted is because this is just y is greater than 2x minus 4. Had it been y is greater than or equal to, then it would have been a solid line. Because there's no equals there, that just means that points that are on this line are not solutions. So which ones are solutions? Anything that is above the line. When you look at this greater than sign, when the y is by itself, you can think of that as standing for above the line. So you'll see that this graph is shaded in all the area above that dotted line. That just means that you can tell if you have a solution based on whether it's in the shaded region. For example, 0, 0, it does appear to be in the shaded region, so I'm predicting that that's a yes. If I wanted you to show your check in the inequality, we're going to plug in a 0 for y and a 0 for x. And 0 is bigger than negative 4, so that was a yes. Let's check 3, 2. Is 2 greater than 2? No, 2 is not greater than 2, so this is a no. I wanted to point that out because see how on the graph the point 3, 2 is on that line, just like it was last time. But because the line is dotted, that just means that it doesn't represent solutions. It doesn't say y is greater than or equal to. For example, if this was 2 is greater than or equal to 2, that would be a yes. But 2 is not greater than 2. A dotted line means no. And then the last one, 5, 3. If we look at it on the graph, you could probably tell right away that it's going to be a no. It's not in the shaded region. If I ask you to show your check, giving you that inequality, ask yourself, is 3 greater than 6? And that is a no. So this is not one of the solutions. Again, there's infinitely many solutions that would be yeses, but we only found one of them. Lesson 2, we're going to start talking about systems of equations and inequalities. That just means that we have more than one equation. In particular, we're going to have 2 equations at a time. So let's look at this first example. In order to be a solution to a system of equations, sometimes you'll see little curly brackets next to there, it has to be an ordered pair that lies on both graphs and satisfies both equations or inequalities. So let's just do a little check. Let's check the point 3, 0. Again, just like last time, we can plug in that x and y and check to see if it's true. It's true for our first equation. We have to check the second equation. And this time 0 does not equal 2. And remember, in order to be a solution, it has to be true for both equations. So that would tell me that this one's a no. If I looked at that point on the graph, the point 3, 0 is only on one of the lines. We know it's this one. It's only on one of the lines. In order to be a solution to the entire system, it's got to be true for both equations. Can you see then that there's really only one solution to this system of equations? Could it be 4, 4? Does that lie on both lines? No, it doesn't. If I asked you to show your check, what if it doesn't work in the very first equation? Do you have to check the second one? The answer is no. If it doesn't work in one of them, we know it's not a solution. Are you thinking that 2, 1 is really the only point that could be a solution here? The only point that's on both lines? So I'm thinking this one's going to be our yes. How would we show our check algebraically? Like this. Since it works in both, I can say yes. For a system of inequalities, remember that we represent these solutions by shading. So here I've got y is greater than x minus 4. That's a dotted line because it's just greater than. And greater than means it's shaded above. And then our other line says y is less than or equal to. So you'll notice that's a solid line because of the equal to. And because it's less than, on that line, we're going to shade below. The question is, which ordered pairs got shaded both times? And because I used sort of a pink and a blue, what do pink and blue make together? They make it purple. So what we say is that this area over here, which actually is an infinite area, it's going to keep going forever, that's where all of our solutions are going to lie. In order for an ordered pair to be a solution, it's got to lie in the doubly shaded region. Let's check 2, 4. The point 2, 4 seems like it works for the red shaded graph, right? Let's check by showing our algebra here. Is 4 bigger than negative 2? Yes. What happens when I check it in the second one? Is 4 less than or equal to 2? No. So if it doesn't work in both inequalities, it is not a solution. What are you thinking about the 6, negative 5? 6, negative 5. That's actually not in any of the shaded area, so that's a pretty clear no to me. I bet I could just plug it into one or the other of those inequalities, and it's going to give me a no right away. Is negative 5 bigger than 2? And that's a no right away, so we can automatically say no there. For the last one, negative 3, 3. That does look like it's in the solution area where both graphs are shaded. Let's double check. 3 is bigger than negative 7. And 3 is smaller than or equal to 8. It works in both. So we showed in 2 different ways that that's a yes, both from the graph and from checking algebraically. Lesson 3 is going to let us find the solutions to our systems without having a graph, without doing trial and error and putting in x's and y's. This first method for figuring out where a line like this one and a line like this one might have a point in common, we're going to try to find that ordered pair where they meet up. The first method is called using substitution, and it's got 4 steps. The first step is solving one of the equations for a variable. And you can choose, do you want to solve the x or the y or the x or the y? There's no right answer to that question, but I do try to be strategic and pick the easiest answer, the one I'm least likely to screw up. This y is practically by itself already. Can you see that if I subtracted 2x from both sides, that y would be it by itself? So I'm going to write that down. I've got this y by itself by doing 10 minus 2x. Then step 2 is to take that and substitute it into the other equation. Since this is what y equals in this case, y equals 10 minus 2x, I'm going to put in the other equation where the y is. And we're replacing the y. The y is going to go away. The y is going to be replaced with a 10 minus 2x. Always use parentheses. That's step 2. Step 2 is substituting into the other equation. Step 3 now is just to solve that equation. You can see that there's only one variable in there. We're going to start by distributing that negative 2. And just solving like normal. What I just figured out is that the ordered pair that is the solution to this system of equations has an x value of 6. That's what I know. I basically know half of the answer. So step 4 is to find the other value. In this case, we need to figure out what y is. We could use any of these above equations and plug in what we know x is. We know x is 6. When doing substitution, I always just pick the thing that I've already solved for. Y is equal to 10 minus 2x. Since now I know what x is, that's kind of an easy pick. Then I find out the y is equal to negative 2, and that completes my ordered pair. And that's the only point that would be a solution to both of those equations, the solution to the system. Let's practice that again on our second example. You have the choice to get this x or this y or this y or this x by itself. I think this x looks pretty easy to solve for, but actually this y is already solved for, right? So we actually don't even need to do step 1. It's kind of done for us. What we do need to do is we need to take the 2x plus 1 and substitute it into the other equation. In this case, since we solved for y, or because the y was already alone, it's going to be subbed in where the y used to be. So instead of x minus 4y, it's x minus 4, and then 2x plus 1. After you've done step 2, you should only have one variable. That's how you know you're doing it right. And we're just going to distribute and solve. Once you find one of your values, you should be able to plug that back in. Again, when I use substitution, I'm always going to use the equation that's already solved. I just find it the easiest. I could plug it into the first equation too. And I get y equals 3. And that means that my solution is the ordered pair 1, 3. There's a single solution. I have one more thing that I wanted to point out. It is possible for one of these solutions to be sort of a trick question. Can we talk about how that might work? Let's say we look at this step right here. What if I combine the x's and for some reason they like canceled each other out? Maybe that was an 8x minus an 8x, and we came up with negative 4 equals negative 11. Like all of the x's disappeared. Does negative 4 equal negative 11? No. In that case, there would be no solution to this system. Literally no ordered pair that would work in both equations. Another possibility is that all your variables cancel out and you get something that is true. You might be thinking all real numbers, but it's not technically all real numbers. There's plenty of ordered pairs that wouldn't work in your equations, but there are infinity answers. So we answer those infinitely many solutions. Just something to watch out for. Lesson 4 is another way of solving a system of equations. It's called elimination. Sometimes you'll hear it called linear combination or even the addition method. It's got one extra step, but oftentimes it's actually a really quick way to solve these. Let's go through the steps together. The first step is to align the equations according to terms. All that means is that all of your x's and all of your y's and your equal signs and your constants are all lined up. And in this case, that's already taken care of. So we're going to go to step 2. We need to multiply one or maybe both of the equations in order to make a set of variable terms opposite. That means we either want the x's to be opposites, like 3x and negative 3x or something like that, or the y's to be opposites. And you might have noticed that the y's, we already have one that's a negative and one that's a positive. But we would need one that's like a negative 4y and one that's a positive 4y to truly have them be opposite. So that's where multiplying the equation comes in. I could multiply both sides of this equation by 4 because I'm trying to turn that y into a positive 4y. I think it's a good idea to rewrite both equations, so I'm just going to rewrite that top equation as it is. And then in the second equation, I'll distribute a 4. And make sure you multiply by 4 on both sides. So that's the same system of equations, it just is written a little differently. And that was step 2. Step 3 is to add the equations together. This seems kind of weird, but you're literally going to add the equations together. 3x plus 20x is 23x. Negative 4y plus 4y is 0y. Don't even write anything down there. And then 12 plus 80, 92. You'll notice there's only one variable. We divide that 23 over, and we get 4. And that actually was step 4. Step 5 is to go back and find that other value. This time, totally up to you which equation you'd like to plug in that x equals 4 into. It could be either of those equations. It could be this one that's multiplied by 4. It shouldn't matter because it should give us the same y value no matter which equation we use. This time I think I'll just use the top equation. So 3 times x, which is 4, minus 4 times y equals 12. And I'm just going to solve that for y. Subtract 12 from both sides. That gives me a 0. Can I do 0 divided by negative 4? I can. It is 0. And that tells me that my solution, my ordered pair, is the point 4, comma, 0. Okay, let's practice on another one. Step 1, remember, was to align the equations. This one does have some alignment issues. My x's are lined up, but the equals aren't. The y's, I guess, sort of look like it. But we need to do some rearranging before we're going to be able to use the elimination method. I actually kind of like how the top equation is set up. It's got the x term, the y term, the equals, then the constant. That's usually how I like mine set up. So if we took the second equation and just subtracted the 5y over, wouldn't that kind of put it in the same form? We'd have 2x minus 5y equals, and that negative 6 would still be over there. That's what I mean by aligning the equations. Next, we have to make sure that one of our variables will eliminate. One of them will cancel. Are 3x and 2x opposites? No. Are 4y and negative 5y opposites? No. But at least the y's have opposite signs, so maybe I'll target the y's this time. Again, you can't choose wrong. I'm just trying to save myself a little bit of work. What if I multiplied the top equation, both sides, by 5, and the bottom equation, both sides, by 4? Can you see my vision? This will be a 20y, and this will be a negative 20y. And that's my goal for step 2. So make sure you distribute that to the entire equation. And now we have one set of variables that has opposites. So step 3 is to add those equations together. This time again, the y's are going to eliminate. And we come up with x equals 2. Now that we solved for one value, we just need to go back and plug that in to find another value. Again, you can pick any of those equations up there. Maybe I'll take the 2 times x equals 5y minus 6. Doesn't matter which equation you use. And I've got y also equals 2. My ordered pair that is a solution to both equations should be 2, 2. And you can always go back and check that. If you plugged in a 2 for the x and a 2 for the y, does the top equation equal 14? It looks like it does. 6 plus 8. And we kind of know it's going to work in the bottom one because we just used that to solve. But that's a nice way to check your work. Kind of like the last lesson, if ever your variables completely cancel each other out and you have no x's and no y's, and that equals 46 or something like that. 0 equals 46 would be a no solution sort of answer. If you added your two equations together and you got something like all the x's, all the y's canceled out, and you also got a 0 on this side, 0 does equal 0, so that would be our infinitely many solutions. And coming soon is the last lesson, solving systems using a graphing calculator.